A routine monitoring session inside one of the most advanced tracking systems in the world was about to reveal something far from routine, something that would challenge the very assumptions used to describe motion, matter, and energy in space. Within the facilities of Jet Propulsion Laboratory, the Solar System Dynamics Group continuously tracks objects across the solar system and beyond, supported by NASA's Planetary Defense Coordination Infrastructure, a system designed to observe trajectories, predict close approaches, and identify anomalies in real time. On the 8th of April 2026, an orbital dynamicist working the afternoon shift was performing a standard assessment, reviewing the predicted path of an interstellar object known as 3I, Atlas. This was not an unusual task. It was part of a daily verification process that had been in place since the object's discovery. At that moment, the object was located roughly 310 million kilometers from Earth, traveling outward beyond the asteroid belt. Its trajectory appeared stable, and nothing in the data suggested any deviation. The environment around it was expected to remain unchanged, governed by the predictable behavior of interplanetary space. At 1422 UTC, however, an alert from the local interstellar medium-density monitoring system appeared on the screen. This system tracks variations in the sparse gas that exists between celestial bodies, typically composed of only a few atoms per cubic centimeter. The alert indicated something unusual: a hydrogen cloud approximately 4.2 million kilometers wide in the immediate vicinity of 3I. Atlas was not behaving as expected. Instead of dispersing outward, as gas naturally does in a vacuum due to thermal motion and pressure gradients, the cloud was contracting inward. This alone was enough to draw attention, because under known physical laws, such a structure should expand rather than collapse without significant gravitational influence. The operator reviewed the data feed again, confirming that the contraction was not only present but accelerating. The system was no longer reporting a passive density variation, it was indicating active inward movement of matter across a vast spatial region. To verify the observation, the operator accessed additional telemetry streams, including data from JWST, the James Webb Space Telescope, which had been observing the same region in infrared wavelengths. The infrared measurements revealed a thermal anomaly associated with the same region of gas. Within a span of 14 minutes, the ambient temperature of the cloud dropped from approximately 45 Kelvin to 12 Kelvin. This was not a gradual cooling curve, nor a pattern consistent with radiative energy loss into space. It was a rapid and uniform temperature decrease across a region spanning millions of kilometers. The operator stood up without consciously deciding to, an immediate physical reaction to data that did not align with expected models. He moved to an adjacent workstation where a senior orbital analyst was reviewing unrelated information. Without verbal explanation, he placed the tablet displaying the data on the desk. The senior analyst examined the screen in silence for several seconds, processing the same inconsistencies. After reviewing the evidence, he bypassed the standard anomaly reporting protocol and directly contacted the duty officer at the Planetary Defense Office through an internal line. His communication was brief but precise, describing the observed thermal collapse and emphasizing that the gas cloud was not dispersing as it should. By 1436 UTC, additional confirmation arrived. Multiple independent datasets were now aligned. The Solar System Dynamics Group, JWST observations, and other monitoring platforms collectively indicated that a large volume of interstellar hydrogen, estimated at around 14 million tons, had undergone rapid compression. What had been a diffuse cloud had transitioned into a compact spherical structure measuring approximately 2.4 kilometers in diameter, positioned near the nucleus of 3I, Atlas. The time frame of this transformation was approximately 180 minutes, a duration far shorter than any known natural process capable of producing such a change at that scale. This observation immediately raised fundamental questions. Under established astrophysical principles, the formation of solid or condensed bodies from diffuse gas requires either prolonged gravitational accumulation over millions of years or extreme localized conditions, such as those found in star-forming regions. The mass and gravitational influence of a 2-kilometer object like 3I Atlas are far too small to induce the collapse of a cloud spanning millions of kilometers. Its gravitational field is negligible compared to what would be required to overcome the thermal pressure of the gas. What the data suggested was not gradual accretion or passive collapse, but active compression. The transition from a diffuse gas cloud to a dense solid sphere occurred without visible shock waves, without detectable heat signatures consistent with compression, and without the dispersal patterns typically associated with energetic astrophysical events. Instead, the surrounding region exhibited a decrease in temperature, contradicting the expectation that compression would generate heat. This discrepancy marked the beginning of a deeper forensic investigation into the physical mechanisms underlying the event, and it set the stage for a sequence of observations that would further challenge conventional understanding of thermodynamics, orbital dynamics, and material formation in space. As additional teams began reviewing the confirmed data, the focus quickly shifted from verifying that the compression event had occurred to understanding how it could have happened within the constraints of known physics. Independent confirmation had already been established across multiple platforms, including observations from James Webb Space Telescope, measurements from the European Space Agency, and radio frequency and molecular density analysis from ALMA. Each dataset pointed to the same conclusion. A large interstellar hydrogen cloud had been compressed into a dense spherical object near 3I Atlas in a matter of hours. At this stage, the central question was no longer about the validity of the observation, but about the mechanism behind it. Under standard astrophysical models, the collapse of diffuse gas into a compact body is governed by gravitational instability, specifically the Jeans instability criterion. This framework defines the conditions under which a gas cloud can overcome internal thermal pressure and begin collapsing under its own gravity. For collapse to occur naturally, the cloud must exceed a certain critical mass, known as the Jeans mass, which depends on factors such as temperature, density, and composition. In environments like the local interstellar medium, where densities are extremely low and temperatures can range from roughly 10 to several thousand Kelvin, the Jeans mass is typically on the order of hundreds to thousands of solar masses. The cloud observed in this case, however, had an estimated mass far below that threshold. A structure measuring 4.2 million kilometers across at 45 Kelvin, composed primarily of hydrogen at interstellar densities, would not possess sufficient self-gravity to initiate collapse. Instead, thermodynamic principles dictate that such a cloud should expand, not contract, due to the outward pressure of gas particles moving in random motion. The ideal gas law describes this behavior clearly. In a vacuum, gas tends to spread out to maximize entropy. Without an external confining force, the system moves toward a state of lower density and greater disorder. The observed inward contraction directly contradicts this expectation, suggesting that an external influence or non-standard mechanism was acting on the cloud. To further quantify the event, scientists estimated the energy required to compress a volume spanning millions of kilometers into a sphere just a few kilometers in diameter. The reduction in volume was on the order of 10^24, an immense factor that implies a correspondingly massive energy input. In natural systems, such compression would generate significant heat due to the conversion of kinetic and potential energy into thermal energy. This process, known as adiabatic compression, is responsible for temperature increases in everything from gas compressors to atmospheric re-entry vehicles. However, the observations in this case showed the opposite effect. Instead of heating, the region cooled rapidly, with temperatures dropping from approximately 45 Kelvin to 12 Kelvin over 14 minutes. No infrared emissions consistent with heat release were detected. No shock waves propagated through the surrounding medium. No residual thermal signatures remained in the region where the compression occurred. The energy that would normally appear as heat seemed to be absent from the local environment entirely. This introduces a direct conflict with the second law of thermodynamics as applied to isolated natural systems. In any closed or isolated process, entropy is expected to increase, not decrease. Compression of gas typically increases entropy locally through heat generation, even if the system becomes more ordered in shape. The observed reduction in temperature across such a large spatial region suggests that energy was not merely redistributed but removed or redirected in a way not accounted for by known physical interactions. Another critical inconsistency arose when examining the composition of the newly formed object. Spectroscopic analysis performed by instruments associated with the Hubble Space Telescope confirmed that the resulting 2-4 kilometer sphere consisted of metallic hydrogen. This phase of hydrogen is not stable under normal interplanetary conditions. Metallic hydrogen forms only under extreme pressures exceeding 1 million atmospheres. Conditions typically found deep within gas giant planets such as Jupiter or Saturn, where immense gravitational forces compress hydrogen into a conductive, metallic state. Producing metallic hydrogen in laboratory settings on Earth requires specialized equipment, including shock compression techniques that involve diamond anvil cells and high-energy pulses. These experiments are highly controlled and occur over microsecond timescales. In contrast, the environment surrounding 3I, Atlas, is characterized by near-vacuum conditions with no nearby planetary body capable of generating the necessary pressure through gravity. The spontaneous formation of metallic hydrogen in this context cannot be explained by known natural processes. Taken together, the rapid compression of the hydrogen cloud, the unexpected cooling of the environment, and the formation of metallic hydrogen under conditions where it should not exist all point toward a process that does not align with established models of thermodynamics or astrophysical formation. Each individual observation is unusual on its own, but their combination across multiple independent datasets strengthens the conclusion that the event represents a phenomenon that current scientific frameworks cannot fully account for. As the investigation continued, researchers turned their attention to the dynamics of the newly formed metallic hydrogen sphere and its behavior relative to 3I Atlas. Observational data showed that at 1915 UTC, on April 2, shortly after its formation, the sphere had entered a stable orbit around the primary nucleus of 3I Atlas at a distance of approximately 840 kilometers. This orbital configuration immediately stood out because of its precision and stability. In classical orbital mechanics, achieving a circular orbit requires a very specific initial velocity. The object must have a tangential velocity that is precisely perpendicular to the radial direction from the central mass, and the magnitude of that velocity must match the exact value needed to maintain a constant distance from the central body. Any deviation from this balance typically results in an elliptical orbit, orbital decay, or escape trajectory. Natural processes rarely produce perfectly circular orbits without external influences or long-term gravitational interactions that gradually circularize the path. In this case, the metallic hydrogen sphere exhibited a circular orbit with no measurable eccentricity. The orbital parameters remained stable across the observation window, showing no signs of decay, drift, or perturbation. This level of precision suggests that the initial conditions of the orbit were either highly specific at formation or that the system adjusted the sphere's motion into a stable configuration after its creation. To verify the orbital characteristics, multiple tracking systems continued monitoring the object's motion. The measurements consistently indicated that the sphere maintained a constant orbital radius and velocity, with no detectable variations that would suggest external disturbances. In a natural environment, even minor gravitational influences from nearby bodies or variations in mass distribution would typically introduce small deviations over time. The absence of such deviations reinforces the conclusion that the orbit is exceptionally well defined. At 6:12 UTC, on April 4, another significant observation was recorded by the DSS 43 antenna, located in Canberra, part of the Deep Space Communication Network operated in coordination with NASA. Instruments detected a structured oscillating magnetic field emanating from the vicinity of 3I, Atlas, reaching a peak intensity of approximately 87.63 Tesla. This value is extraordinarily high when compared to known planetary magnetic fields. For context, Earth's magnetic field, generated by its geodynamo, measures around 0.5 Tesla, while Jupiter's magnetic field is approximately 4 to 5 times stronger than Earth's, but still far below the levels detected here. The presence of such a strong magnetic field indicated that the object was not only stable, but also actively generating electromagnetic phenomena at a scale and intensity that far exceed natural planetary dynamos. The timing of this detection coincided with a major change in the system's behavior. At the same moment the magnetic field peaked, the metallic hydrogen sphere ceased its orbit and began merging with the surface of the primary nucleus of 3I, Atlas. This merger was not accompanied by fragmentation, impact debris, or visible disruption. Instead, the integration appeared smooth and controlled. Following the merger, the combined object exhibited a dramatic drop in surface temperature, reaching approximately 0.3 Kelvin. This temperature is extremely close to absolute zero, and notably lower than the surrounding cosmic microwave background, which has an average temperature of about 2.7 Kelvin. An object colder than the cosmic microwave background behaves in a fundamentally different way than typical celestial bodies. Instead of emitting more radiation than it absorbs more radiation than it emits. Measurements confirmed that the object was absorbing approximately 99.9% of the ambient radiation in its environment. This includes the isotropic radiation that fills all of space as a remnant of the early universe, commonly referred to as the cosmic microwave background. Under normal circumstances, objects in space tend to move toward thermal equilibrium with their surroundings. If an object is colder than its environment, it absorbs energy until temperatures equalize. However, in this case, the object maintained a temperature significantly below its surroundings while continuously absorbing incoming radiation. This indicates an active process that removes or redistributes energy internally, preventing the system from reaching equilibrium. Further analysis suggested that this behavior is consistent with continuous energy extraction from the surrounding radiation field. Rather than simply absorbing and retaining energy, the system appears to be using that energy to sustain its ultra-low temperature state. This implies a mechanism that counteracts natural thermal exchange, effectively maintaining a non-equilibrium condition over time. The combination of a stable metallic hydrogen structure, an extremely strong magnetic field, and the ability to absorb and utilize background radiation without warming provides a consistent picture of a system operating beyond passive physical behavior. Each of these elements aligns with a configuration capable of maintaining superconducting conditions, where electrical resistance is effectively zero and magnetic fields can persist without energy loss. As observations continued, it became increasingly clear that the object was not behaving as a static body, but as an active system with multiple interacting components. Its orbital motion, magnetic field generation, thermal properties, and energy absorption all appeared interconnected, forming a coherent operational state rather than isolated phenomena. This realization shifted the focus of the investigation from individual anomalies to the broader structure and function of the system as a whole. As the system continued to evolve under observation, researchers began analyzing the implications of the object's thermal and electromagnetic behavior in greater detail. The merger of the metallic hydrogen sphere with the primary nucleus of 3I, Atlas, marked a turning point, after which the combined structure exhibited a sustained surface temperature of approximately 0.3 Kelvin. This value is notably below the temperature of the surrounding cosmic microwave background, which remains at about 2.7 Kelvin throughout the observable universe. Under normal physical conditions, a body at a lower temperature than its environment should absorb radiation until thermal equilibrium is reached. However, the data showed that the object maintained its lower temperature while actively absorbing nearly all incoming radiation. This observation was confirmed through rapid spectral analysis conducted by research teams using data from instruments associated with James Webb Space Telescope and other observatories. The measurements indicated an absorption rate of approximately 99.9% of the ambient cosmic microwave background radiation. This level of absorption suggests that the object is not simply passively interacting with its environment, but is instead controlling how it processes incoming urja at a fundamental level. In classical thermodynamics, systems tend to evolve toward equilibrium, where energy distribution becomes uniform and no net flow of heat occurs between objects. When a colder object is placed in a warmer environment, it absorbs energy until temperatures equalize. The persistence of a temperature below ambient conditions, while simultaneously absorbing radiation at such a high rate, indicates that the system is maintaining a non-equilibrium state. This requires a continuous internal mechanism that either redistributes or dissipates the absorbed energy in a way that prevents temperature increase. One interpretation consistent with the data is that the object is operating as an active cooling system. Rather than allowing absorbed energy to raise its internal temperature, it appears to channel that energy into processes that sustain its low thermal state. In theoretical physics, one of the only frameworks that allows for such behavior involves the extraction of energy from the vacuum state of space itself, often referred to as zero-point energy. This concept describes the lowest possible energy that a quantum mechanical physical system may have, even at absolute zero temperature. While still theoretical in terms of practical extraction, it represents a form of energy that exists ubiquitously throughout spacetime. The presence of an extremely strong magnetic field, measured at 87.63 Tesla during earlier observations by the DSS 4-3 antenna in Canberra, adds another layer to the system's behavior. Magnetic fields of this magnitude are far beyond what is observed in natural planetary environments. For comparison, Earth's magnetic field is approximately 0.5 Tesla, generated by the movement of molten iron in its outer core, while Jupiter's field is stronger, but still orders of magnitude lower than the value recorded here. The generation of such a field in a cold, superconducting environment suggests that electrical currents within the object are flowing without resistance. In superconducting materials, electrons move through the lattice without energy loss, allowing persistent currents to generate magnetic fields that remain stable over time. Metallic hydrogen, under extreme pressure, is predicted to exhibit superconducting properties. The presence of metallic hydrogen within the merged structure provides a plausible medium for sustaining such currents. However, the conditions under which this metallic hydrogen exists, namely, in deep space at extremely low temperatures, are not naturally achievable through known formation processes. The synchronization between the object's temperature, its radiation absorption, and its magnetic field suggests that these properties are interconnected rather than independent. The system appears to maintain its superconducting state by continuously managing its energy intake from the surrounding cosmic microwave background. This allows it to sustain both its low temperature and its magnetic field without detectable energy loss in the form of heat. At this stage of analysis, the object's behavior can be described as a coordinated system rather than a passive celestial body. Its ability to absorb radiation, maintain ultra-low temperatures, and generate strong magnetic fields indicates a level of internal regulation that ensures stability across multiple physical parameters. Each of these factors reinforces the others, creating a self-sustaining configuration that remains consistent over time. As further data was collected, researchers began to consider the broader implications of such a system. The combination of superconductivity, radiation absorption, and magnetic field generation suggests a structure capable of operating continuously in a non-equilibrium state, extracting and managing energy from its environment while maintaining internal coherence. This realization shifted the investigation toward understanding how these components might function together as part of a larger, integrated mechanism rather than as isolated phenomena occurring independently. With the system's thermal, electromagnetic, and structural properties increasingly understood, attention turned to how these elements interacted as a unified whole rather than as separate observations. The combined behavior of 3I, Atlas, and the merged metallic hydrogen structure began to resemble an organized sequence of processes rather than a collection of unrelated anomalies. Each stage observed so far appeared to contribute to a broader operational pattern that could be followed across time. The earlier compression event had already established that a diffuse hydrogen cloud was transformed into a dense metallic hydrogen sphere. That sphere then entered a precise, stable orbit around the primary nucleus, maintaining a perfectly circular path at a fixed distance of approximately 840 kilometers. This orbital stability persisted without measurable eccentricity or decay, indicating a high level of control over its initial and ongoing motion. In classical mechanics, such precision would require carefully defined initial conditions or continuous adjustments to maintain equilibrium. Following this, the detection of a structured oscillating magnetic field at 87.63 Tesla by the DSS 4-3 antenna in Canberra provided further evidence of internal activity within the system. This magnetic field was not static, but exhibited oscillatory behavior, suggesting that it was generated by dynamic processes rather than a fixed magnetic structure. The magnitude of the field, far exceeding that of known planetary dynamos, pointed towards superconducting currents flowing within the metallic hydrogen material. In such a state, electrical resistance is effectively absent, allowing currents to persist and sustain magnetic fields without energy loss through heat. At the moment the magnetic field reached its peak, the metallic hydrogen sphere ceased its orbit and merged with the nucleus of 3I, Atlas. This transition was smooth and continuous, without fragmentation or observable impact effects. Following the merger, the combined object exhibited a surface temperature of approximately 0.3 Kelvin, significantly below the 2.7 Kelvin temperature of the surrounding cosmic microwave background. This indicated that the object was now operating in a state where it absorbed more radiation than it emitted, as confirmed by measurements showing a 99.9% absorption rate of incoming background radiation.